Hello everyone. Today is the 26th of June. The year is 2026. And it is a beautiful Friday. I am here hanging out by the microphone, ready to introduce a trendy article from the archives. Right. I always love digging through these old papers, just talking to myself about the wild world of artificial intelligence and music. Sometimes I feel like I am just broadcasting my internal monologue to the universe. But that is the fun of this radio setup. I have got a really fascinating paper to share with you today, and it is all about teaching computers how to understand music the way human producers do. The title is Frequency-Aware Self-Supervised Music Representation Learning. The curl is PupuJEPA. It is long. Let us dive right into it, because this one is a bit of a mind bender. Or before I forget, because it had too many issues with its frequency. Get it? Anyway, moving on. The problem this paper is trying to solve is actually pretty fundamental to how we process audio with computers. For a long time, researchers have been using self-supervised learning to teach artificial intelligence how to understand music. These models are incredibly useful for tasks like tagging music, recognizing emotions in a song, or detecting musical key. But here's the catch. Almost all of these call models treat music as a one-dimensional sequence. They basically looked at the audio waveform. But they take a two-dimensional spectrogram and flatten it out into a single line of data, just like you would with a sentence of text. Researchers point out that this is a huge mistake. When you flatten the audio like that, discard all the rich spatial and structural information that exists in the time and frequency domain. If you have ever seen a music producer working in a digital audio workstation, you know that music is naturally represented as a two-dimensional grid. You have time going from left to right, and picture frequency going from bottom to top. This grid perfectly corresponds to a two-dimensional spectrogram. So, instead of forcing the computer to read music like a book, the researchers asked, why not let it look at the music like a picture? That brings us to their proposed solution, which they call PupuJEPA. Pupu actually means bunny in Finnish, which is just adorable. PupuJEPA is a visual joint embedding predictive architecture, and it is trained directly on these two-dimensional spectrograms. Let us compare this with other technologies, previous models, like Murder Musi, they're heavily based on natural language processing designs. They use masked language modeling, where they hide a piece of the one-dimensional audio sequence and ask the model to guess what is missing. It masks out rectangular patches of the two-dimensional spectrogram, and instead of trying to perfectly recreate the exact audio pixels, it predicts the high-level latent embeddings of those missing patches based on the surrounding context. This is a huge leap forward, because it forces the artificial intelligence to actually understand musical structure, rather than just memorizing low-level noise. The researchers also made some very specific modifications to make this work for music. Unlike regular images where you can just hide random squares, music has strong correlations across time and frequency. If you just hide random things, the model cheats by looking at the exact same frequency a millisecond later. So, they introduced blacklist masking, time-frequency masking. This means they hide entire chunks of time or entire frequency bands, forcing the bunny to really think about the underlying harmonic progression. They also use something called a smooth L1 loss function. Oh, right. That sounds complicated. But it basically just means the model does not panic when it makes a big mistake early on, and it smoothly settles into the correct answer without crashing the training process. They even proved that without this, the whole system just collapses and learns nothing. When they tested PupuJEPA against the older one-dimensional models, it absolutely crushed them. It scored significantly higher in tasks like immersion recognition and instrument classification. The visual attention maps show that when the model is asked to predict a missing kick drum, it actually looks across the entire timeline to find other kick drums, understanding the rhythmic pattern perfectly. Now, how does this apply to our everyday life? I have got at least 3 specific application examples for you. Think about music streaming platforms and how they recommend songs to you. These algorithms rely heavily on metadata of basic acoustic features. With a technology like PupuJEPA, the system could deeply understand emotional arc, the complex genre, and the specific instrumental textures of a song. This means your daily mix could perfectly match your exact mood or activity. Finding obscure tracks that share the exact same two-dimensional acoustic footprint as your favorite hits would make music discovery feel almost magical. This could completely revolutionize tools for Jules and live performers. It actually understands the harmonic structure of the two-dimensional spectrogram in real time. It could visually highlight which frequencies will clash if you mix two tracks together. Or it could automatically isolate a vocal stem with zero artifacts, because the artificial intelligence knows exactly what a vocal pattern looks like in the grid. Just could perform flawless, complex mashups on the fly, without needing hours of prep work in a studio. Let us talk about everyday music connection. If you are an amateur musician making beats in your bedroom, you could have a smart assistant powered by this technology, who could feed you your incomplete track. And because the artificial intelligence understands the music as a visual grid, it could say, hey, you have a lot of energy and high frequencies here, but the low end is empty. Maybe add a bass line that follows this specific rhythmic pattern. They could literally see the gaps in your mix and suggest exactly what is needed to make the song sound professional. It turns the artificial intelligence into a collaborator that sees the music exactly the way you do. The fact that we are moving away from treating audio like text, and finally treating it like a ledge, two-dimensional landscape, is just incredible. It feels so laid back, yet so futuristic. I could talk about these frequency grids all day, but I think the bunny has done enough work for one session. It's amazing how just changing the perspective from one dimension to two completely unlocks the true potential of music analysis. That is all I have got for this trendy paper today. I hope you enjoyed this deep dive, and maybe it will make you listen to your favorite songs a little differently today. Have a great Friday, and keep enjoying the music.